Welcome to the third video of the module 2, that is conformal transformation and complex integration. In this video, I am going to explain the Cauchys theorem, consequences and the problems based on that. Green's theorem. Before going to the Cauchys theorem, let me explain what is Green's theorem. So the Green's theorem in a plane is, if R is a closed region of the xy plane bounded by a simple closed curve C, and if m and n are two continuous functions of x and y having the continuous first order partial derivatives in the region R, then the integral along C of m dx plus n dy is equal to double integral along the region of dou n by dou x minus dou m by dou y into dx dy. This is the Green's theorem in the plane. So now let us do the Cauchys theorem. The statement of the Cauchys theorem says that if f of z is analytic at all points inside and on the simple closed curve C, then integral along C f of z into dz is equal to 0. This is the statement. Proof. Let f of z is equal to u plus iv is analytic. This implies integral of f of z into dz is equal to integral of u plus iv into dx plus I dy. That is, on multiplication, that is u plus iv, when I multiply this with dx plus I dy, what do I get it? That is u dx plus u into, that is I into u dy plus iv dx minus v dy. So this is the real part and the last one, therefore u dx minus v dy, and the imaginary part is separated, that is v dx and u dy. Let us call this as equation number 1. Now we can use the Green's theorem, where the Green's theorem is nothing but m dx plus n dy, which I have already stated, under the along the integral of the curve is given by dou n by dou x minus dou m by dou y dx dy along the region here. So let us apply the Green's theorem for this in the equation 1. So the equation 1 implies integral along C of f of z dz is equal to double integral along R of minus dou v by dou x minus dou u by dou y into dx dy plus I into double integral along R of dou u by dou x minus dou v by dou y into dx into dy. But since it is an analytic function, from the CR equations we have dou u by dou x is dou v by dou y and dou v by dou x is minus of dou u by dou y. So the equation will reduce to minus dou v by dou x plus dou v by dou x, which cancels and it will be 0. Here also we have dou u by dou x minus dou u by dou x, which again it will become 0. Therefore, integral along C of f of z into dz is equal to 0. Hence it is proved. Next, let us discuss the consequences of the Cauchys theorem. First consequence, if f of z is analytic in a region R and if p and q are any two points in it, then integral from p to q f of z dz is independent of joining a path joining p and q. That is, integral from p to q p f of z dz is same for all curves joining p and q. That means, let me just illustrate. See, p and q, it is going in this path as C1 and another path it is C2. There are only two fixed points, that is p and q. One path is in this direction. All are going in the p to q only. Another path is this. Another path is this. So it is immaterial whether you are following the curve 1 path curve 2 path or curve 3 path. Any path if you follow also, it will be the same. That is what is the first consequence is. So look at this one. It is f of z along C1 is dz is equal to f of z dz along the C2. Here you can see the difference. Along C1 is same as along C2 also. That is what is the first consequence says. No proof of that is required. Second consequence what it says is, if C1 and C2 are two simple closed curves such that C2 lies entirely in the C1. You can observe here, this is the C1, the outer one is C1, the innermost curve is C2. If C2 is lying inside the C1, then, and if f of z is analytic on C1 and C2 and in the region bounded by C1 and C2. How this bounded by means? See here, this is the curve C1 outside. Another curve is C2. Okay, this we will call it as the annular region. So it is the region bounded by the two curves C1 and C2. Then along C1 is same as along C2. If it is bounded by the two curves, say C1 and C2. Next one. The third one. If C is a simple closed curve enclosing the non-overlapping simple closed curves C1, C2, etc. Cn, and if f of z is analytic in the annular region between C1 and these curves. So, how it will be means, this is the one curve and in between only one curve has been added. So many more curves will be there. Okay, so C1, C2, C3, C4, etc. Cn. Many more curves will be there in the annular region between C and these curves. So what is the annular region here means? The region generated between the boundaries of the first curve, that is C, to these curves which are there inside. Then integral along f of z dz is equal to C1 f of integral along C1 of f of z plus integral along C2 f of z plus integral along C3 f of z, etc. Integral along Cn into f of z dz. This is what it says about the third consequence. Proof. Verify the Cauchys theorem. Problem. Verify the Cauchys theorem for the function f of z equal to z square where c is the square. Anyway, this problem I have already explained in the previous class. So, previous video. So, the same, the curve will be same, but here we need to verify this. So, from the Cauchys theorem, we have f of z under the integral c is equal to 0. So, the curve is same 0, 0, 1, 0, 1, 1 and 0, 1, which is moving from 0 to A to B, B to C and C to O. And you know already what are the variations, that is x is varying from where to where in the direction of 0 to A, O to A to B, etc. So now along the curve, that is square OABC, and f of z is equal to z square. So this implies what? According to the consequence, it is along OA plus along AB plus BC and CO, which is equal to 0, that we need to prove. And we know that z is equal to x plus iy and dz is equal to dx plus I dx. Therefore, z square into dz will be x plus iy whole square into dx plus I dy. Now, let us look into along the OA what happens. Along OA means, I will just draw and show you. Along OA is this path. Therefore, y will be 0 because it is in the it is aligned with the x-axis. So, y is 0 and y is 0, dy will be 0 and x varies from 0 to 1. We can see here, this is the point here and this is another point, that is 1, 0. So, y is already fixed and x is varying from 0 to 1. So, we get on simplification x square dx is integration is x cube by 3 and which gives us 1 by 3. Next, let us take along AB. So along AB, if you are taking x is equal to 1, so a dx is equal to 0 and y varies from 0 to 1. So when we substitute, which you have already done this problem, so it will be 1 y minus y cube by 3 plus 2i y square by 2 and the limits are from 0 to 1. Therefore, 1 minus 1 by 3 plus I, that is 2 by 3i minus 1. Next, along BC if we take, what we are getting is y is equal to 1 and dy is equal to 0, x is varying from 1 to 0, which on simplification x plus I whole square into dx, or this is nothing but 2 by 3 minus I we are getting. Next, along CO if we are taking, then we are getting x is equal to 0 and dx is 0 and y varies from 1 to 0. Therefore, z square dz is equal to y into y to z, y is equal to 1 to 0, iy square into I dy, that is minus I into y is equal to 1 to 0 of y square dy. This on integration we get minus y cube by 3 and 1 to 0. Therefore, once again it will be minus. Minus of minus it will be plus. Then we will be getting plus I divided by 3. This is the answer we are going to get it along CO. Next, we need to add all these values and we need to prove that it is equal to 0. Therefore, 1 by 3 plus 2 by 3i minus 1 plus 2 by 3 minus I plus I by 3. When we simplify everything, we will be getting it as equal to 0. Hence, it has been proved. It's verified. Thank you.